Welcome back. I just realized as I was watching this delightful video that this is a mistake. I just ended this one. This is a contrary. It says -1, so that should have gone right, not left. So this should have been right 1 up 2. Be nice if your instructional videos could be correct. Anyway, I'm going to do another one of those later, but that was wrong. Thank you all for correcting me. I know you were. I just didn't hear you. So, okay, let's move on. Stretching and shrinking. Let's go back to our famous graph of y equals x squared, which we keep using because we're so familiar with that. I wanted to show you what happens when you we've talked about what happens when you add 2, you go up and down vertically. When you put inside a plus or minus, you go left and right horizontally. What happens if you stick a number in front like y equals 3x squared? And what if you put something smaller than 1 like 1/3 x squared? Well, to demonstrate, I'm just going to show you all three graphs on the same coordinate axis. So here's the original, y equals x squared. You know, the whole thing, 0, 0, the whole thing. If you put a multiplier in front of it, like this, that is going to have the effect of stretching. And what stretching is going to do is it's going to draw that graph in closer to the y-axis. In other words, it's going to make it taller. That is a horrible picture. I'm looking at that thinking, oh my goodness, it must be late at night. This is y equals 3x squared. Now the reason this looks like this is, you know how this point 1, 1 was on the original graph? Well, here the graph point would be 3, 1. No, sorry, 1, 3. 3 times as big. So instead of 1, 1, you'd go to 1 and make it 3 times as tall. So in other words, it's the equivalent of making him 3 times as tall, and he would stretch towards the y-axis. On the other hand, if the multiplier is a fraction, something less than 1, you're going to stretch the guy out. So he's going to be more like flat, like this. So that's the difference. A number greater than 1 is going to stretch. That's greater than 1. And a number less than 1, but still greater than 0, a positive number less than 1, a fraction, is going to shrink. Let me draw a better picture. Let's do one more example. Suppose we're going to do y equals, let's do cube root because we never do it. So cube root x, and then y equals 4 cube root x, and then y is equal to 1/2 cube root x. And let's just put all those 3 here on one axis and see if I can make this look anywhere close to nice. Here is the original cube root. Cube root is kind of a flat snake. You know, he doesn't do much. Now, if we're going to stretch him, we're going to make him 4 times as tall. What's going to happen is he's going to pull in like kind of like this towards the y-axis. He's going to get taller. This point that was 1, 1 is now going to be 1, 4. So this was 1, 1. Now he's 1, 4. So he's going to get taller. That is this one. Now, if you want to flatten him out, I'm going to dot that one. It would look kind of like this. Draw him toward the x-axis. So that would be the flatter one. So this is the stretch and the shrink, a multiplier in front of a graph. Okay, so we've vertically shifted, we've horizontally shifted, we've stretched, we've shrunk. Now the last thing, let's talk about reflecting these graphs about the axis, flipping, if you will. All right, now let's look at our best example to show reflection is the only graph that we've talked about that is not symmetrical about the origin or the axis. It's not even or odd. Let's take the graph y is equal to the square root of x. This is one of my favorite graphs because I can show all kinds of things on this graph. Here is the basic. Remember, it's the one wing. one wing guy. Now, a reflection like this, a negative on the outside of the graph. Notice I'm gonna mark that for you. It's on the outside. Is going to do the same thing as when you stick a negative outside of the x square of a parabola. It's going to flip it down. So when you see a negative on the outside, here's the definition officially. You're going to reflect or flip across the x-axis. Now, I don't worry too much about that. I just know that when I stick a negative in front of a parabola, it turns it down. So when I stick a negative in front of any function, it is going to flip it this way across the x-axis. So there is the graph of y equals negative square root of x. This is the graph of y equals square root of x. Now, if you put the negative on the inside, which would be this, you're going to flip it across the y-axis. This is reflect across the y. And so that, let me get my green pen, is going to look like this. Well, it was supposed to look a little better than that, but you know the basic idea. So that is that one. Reflects across the y on the inside. And of course, if you did them both, you would be flipping and turning and you'd end up down here, but that's another day. Now, some graphs don't reflect. For example, our most favorite graph, y equals x squared. Look what happens to it. Here is normal, okay? Now, if I stick a negative on the outside of that, let me use my red here, y equals negative x squared, like that. You know exactly what happens to that. It goes down, you know, like parabola opening down. But if I put it on the inside, let's go over here, y equals, put it on the inside and square it, well, then you know that negative x squared is the same thing as x squared. So basically, when we flip it this way, it's itself. It doesn't change. So it looks exactly the same. This is a characteristic of even functions. Even functions do not reflect across the y-axis. They do reflect across the x. So you don't really even see any change. The same thing, look at cube. Y equals x cubed. Okay, this is cube. You know, that's basic cube. Now, if we reflect it across the x-axis, it is going to reflect down here and up here. In other words, this piece goes down, this piece goes up. That is y is equal to outside x cubed. Okay? Now, if I do y equals inside x, negative x cubed, I'm going to get exactly the same thing. So these two graphs are the same. You know, whether you reflect this, if you spin it this way or if you spin it this way, they're both the same graph. And you can see why, because negative of x cubed and negative x cubed are both going to give you negative x cubed, same thing. So this one right here is my favorite to show on the reflections because it's the only one that actually changes every time you reflect it. Okay, now the last thing I want to do, and I've got about 5 minutes, so we're going to play just a little game that we're going to play called Name That Function. And the way this game will be played is I will show you a graph and I will ask you to tell me the function. Rather than always giving you the function and asking you for the graph, I might want to give you the function and you tell me or I'll give you the graph and you tell me the function. For example, suppose you see this picture, and this is a point, and it is at 5, 6. And so you would say, well, that is a x squared graph. That is a problem. So it used to be here. But what has happened to it? Well, it has moved right 5. It has moved up 6. Now, how do I write that? How do I write that in terms of a function? So it used to be y is equal to x squared. Okay, used to be that. But now it has moved right 5, which would be y equals x minus 5 squared. That's how we do right 5. And then it's moved up 6. So here, this should be the answer. Y is equal to x minus 5, the quantity squared. This would get it right 5, right there, right 5. Remember, it's inside and contrary in direction. This would get it up 6. Now, when we play this game, we will assume that we are not going to stretch and shrink them, because that's hard to tell, especially on these graphs that I draw, that I just sketch. So it's hard to tell. So we won't use vertical and horizontal stretch and shrinks. Okay, let's do one more of those, and then that will be all for this lesson. So suppose you see a picture, and it looks like this. And again, we're going to assume no stretch and shrink. This is the point 8, -3. And that's your function, and that's your graph, and you need to name that function. So what we've got was an absolute value. That's what it started out looking at. And so it looks like to me it was that, but then we turned it over, which means we stuck a negative in front of it, and then we moved it over 8 and down 3. So it is right 8, it is down 3, and it is flipped across. It is a reflection across the x. All right, so we can see what that would be. So the answer should be y equals absolute value of x. All right, right 8 would be -8, -3, and I think the negative goes out there. Now let's check. That would be -8. So this would go to this, would go to this, and then would flip it down. I think that's right. Let's see if that point works. If we had an 8 in there, 0, -3, I think that's right. Anyway, this is what we're going to do for the next couple of days. This will kind of round out the week. We'll be doing a lot of graphing. And again, the more we do, the better we get. And remember, you've got your graphing calculator that you can back it up with. And again, you need to practice using that because you paid for it and we need to make it effective. Okay, this is the second part of video 1-3, and I will see you next time. Thanks.